Alright guys, I wanted to talk about this problem today on the snow day so you didn't waste your entire snow day studying it, because it's really difficult and there's some tricky stuff that happens at the end. If you remember, the problem is we have a kilolumen light bulb and a 500 lumen light bulb separated by 4 meters, so R equals 0 and R equals 4. And I asked you, where's the dimmest point R? So this is an optimization problem. So in other words, we're going to set a derivative equal to 0. And specifically, we're going to set the derivative di dr equal to 0. That's the whole point of this problem, where I stands for intensity, or light intensity, and R is the distance between the two. And we're using R instead of X because in general, light sources are radial. It doesn't matter like which way you go away from them. They all decrease kind of the same way if it's easy. Or, I'm sorry, not easy, if it's like a sphere or something like that. So anyways, we'll use R instead of X. Anyways, so let's get going. I gave you that the general intensity of a light bulb is its intensity over the radius squared between the two. So this is a bit of physics here. And basically all that's saying is that the intensity of the light bulb drops off as you get away. So as R gets bigger, the intensity gets smaller. And this is really common in physics to have a something over R squared, because that represents something that's like spreading out on a circle. And just like light does, you can see here it's spreading out on a circle. So there's less arrows in this circle than there are in this circle. It's another way to think of it. Okay, so we need to create a function that represents both of these light bulbs. Well, the first one is easy. So here's the I for the whole system. We've got the 1000 lumen light bulb divided by R squared. So no matter where we are on this R line, we're going to take 1000 divided by R squared, and that's going to be the brightness, it seems to us, of the this light bulb right here. But this one's confusing, right? It's shifted over by 4. So we're going to have some goofy stuff in its R. And I'm pretty sure I showed you this last time we had school, which is I don't know when, that this one's going to be R minus 4 squared. So all we did was take the exact same formula, I0, and shift it over by 4. Okay, so now we need to find di dr. So that's a really simple derivative. So d dr on both sides. Like so. And then this derivative comes out to be, of course, di dr, which is the thing we wanted. How does the intensity change in R? And then these ones right here all have negative exponents. So this one right here is a negative 2. So when I do its derivative, I'm going to get a negative 2 to come down and make a negative 2000. And then I'm going to subtract 1 from negative 2, which is going to yield me R cubed. This one is a chain rule, but it's a really simple chain rule. So the negative 2 is going to come down and create a negative 1000. And then this is going to become a negative 3. But then we have to finish the chain roll off because there was some stuff in here. But this stuff is really simple. It's a line of slope 1. So we just end up with a 1 minus 0 because the derivative of 4 is 0. So that doesn't really change anything. So up here, we end up with di dr equaling negative 2000. I'm sorry, you guys can't see that. Divided by R cubed minus 1000 over R minus 4 cubed, like that. Okay, so now we have to set that equal to 0. So now optimize it. This is the derivative. So you could be done if you were just looking for the derivative, but we're not. We're trying to optimize it. So set 0 equal to negative 2000 R cubed minus 1000 R minus 4 cubed. We can't really cancel anything, but we can find common denominators because these have separate denominators. So this side needs this crazy denominator. So we're going to end up with negative 2000 times R minus 4 cubed. And then this side's going to get an R cubed. So we're going to end up with minus 1000 R cubed. The whole thing divided by R cubed R minus 4 cubed. So that's our whole thing. And then we can abuse the denominator into the 0. So multiply both sides by the denominator, and that disappears. So we end up with 0 equals negative 2000 R minus 4 cubed minus 1000 R cubed. that's where we end up. And that's kind of not the best place to be, and we'll see why in a second. So we have this equation right here. And now our only choices are to attempt to FOIL this out, and hopefully things cancel and solve for r. So we end up with 0 equals negative 2,000 r minus 4. And I'm going to do it in 2 stages. So I'm going to FOIL 2 of these out. So r squared minus 8r. And then plus 16 minus 1,000 r cubed. And some of you are probably saying, hey, couldn't you divide by 1,000? Right? This piece has 1,000, and all of these are multiplied by 2,000. Yeah, I totally could, especially because there's a 0 here. So if I divide everything by 1,000, I end up with 0 equals negative 2 minus 1 r cubed. So that's good. Let's finish this triple distribution out here. So I end up with r cubed minus 8r squared, and then plus 16r. So we've done all the r's. Now let's do the 4. So we get negative 4r squared, and then this one we get positive 32 r, and then this one we get negative 40 plus 24, so that's negative 64, right? Hope so. Yeah. All of that minus a single r cubed, because remember we divided 1,000 off of both of these pieces. So this one became a 2, and this one went to 1,000, or dropped to 1 from 1,000. Okay, so we can distribute this 2 in, and you can see here that things are not looking up for us. We have negative 2 r cubed plus 16r squared minus 32r plus 8r squared minus 64r plus 128 minus r cubed. So I've factored in an opposite sign 2 into all of these pieces. And you can see here we got some problems. So this is going to go into here and make a negative 3. These two are going to combine to be a positive 24. So we end up with 0 equals 3r cubed negative plus 24r squared. And then we have a couple of these, so that's going to make what, a 96? 96r, and then plus 128. Well, this is a problem because not many people know how to solve a cubic like this, and it's fairly involved. I'm not sure whether you guys did it in pre-calc, and we're not going to. So you actually get to a point where you are stuck unless you really want to spend like probably 2 hours figuring out how to turn this into a quadratic with a substitution for these r's. And that's really not something that would be worth our time. And the reason I show you this problem is that I'd like you to be able to identify when you are stuck. So that's just as important as being able to solve the problem. And I know I just said that and you're not going to believe me. You're going to say, yeah, right, you just want the right answers. Well, no, I don't. It's really important that you know when you can't do something so that you know when to apply the appropriate technology. So if you are now switched to Grapher using this, you can get a much more specific answer than just sort of approximating the 0 point on the original graph. And you end up seeing something that looks a little bit like this, which crosses 0 right here. So this is the graph of this. So this spits out a 0 here, which is about at 2.22. So I would use a graph. You could also start to guess numbers and make a table and figure that out. But it's really important that you recognize I'm stuck here, unless I know a lot about cubics, which most of us don't. Okay, so the final answer makes some sense. The final answer is that about 2.2 meters from the bright one, so this is at 2.2 right here, meters, which makes perfect sense because I'm going to be the dimmest once I start to get into the field of influence of the lesser light bulb. And this is really interesting mathematics. This same mathematics applies to gravity, it applies to atoms, it applies to electricity, it applies to magnetism. You might ask the question, where is the weakest gravity point between the moon and the Earth? And that would be almost the exact same problem as this one that we just did, because all of these things are described by fields. And those fields decrease with this 1 over r squared. They all kind of go like this, because the further away you get, they have to spread out their force fields over more area and volume. So if you're interested in that, let me know. We can dig into that a little bit more. All right, team. I hope you're enjoying your cold weather day. Please don't get frostbite or do anything silly outside on snowmobiles. And we'll see you guys tomorrow.